Good afternoon viewers and welcome to the EduSat lecture for the science stream. Today we have with us Dr. Pankaj Khanna from the Acharya Narendra Dev College, University of Delhi. We are going to a journey of stereochemistry with wonderful models he has with us, and we will be learning about the history of stereochemistry and the various types of stereochemistry. So we welcome Dr. Pankaj Khanna to our studios.
Hello viewers, welcome to the lecture on stereochemistry. Basically I am talking about stereochemistry in terms of the history and the learning we get from the stereochemical aspects. So there are a few ways of doing stereochemistry, but my way of doing is not mainly with models, but with the visualization we can do in a natural way. So what I am trying to suggest is, like, we can start with stereochemistry in a way we can do it in an atmosphere where we can see atoms and molecules. So to start with the presentation, first of all, that we can see the slide, the topics to be covered today. I would be briefly starting with specific rotation to give you a feel of what we are talking about. The historical perspective, the chirality and enantiomerism topic, then how we got the tetrahedral carbon, and last but not least symmetry elements. So how does stereochemistry evolve? Stereochemistry evolved with a term which is called as stereos. As you can see in the slide, stereochemistry can be divided into two parts. Number one is stereo, which means solidity or three-dimensionality of a molecule per se, and chemistry word gives the chemistry part of it. So it is nothing else but the chemistry in 3D space. 3D space means that we are looking at the molecules, how they are actually present in the system. Further, we may also define stereochemistry as study of stereoisomers, which is the similar structure but different arrangement in space. Because I have used the term stereoisomers, so I would like you to briefly see what are the types of isomers which may be present. You may be knowing it, but you should know beforehand that the isomers are those compounds which have the similar molecular formula but different structural formula. So they may be divided into, first classification is on the basis of their structure, constitutional isomers and stereoisomers. What are constitutional isomers? I am not going into detail of constitutional isomers because my topic does not say so. Constitutional isomers are those isomers which have the same molecular formula but a different structure. Say if I am having a chain of 4 carbons, I can have N-butane or isobutane. So the chain length is varying, branching occurs, and we have chain isomerism. Then we can have a position isomerism, kind of 1-chlorobutane or 2-chlorobutane, and so on. There are 5 to 6 types of constitutional isomerism which may again be said to be structural isomerism, another word for constitutional isomerism. So chain isomerism, metamerism, and so on. But we are focusing here on stereoisomerism. Stereoisomerism can further be divided into conformational isomerism or configurational isomerism. Conformational isomerism arises when we are doing the rotation around a carbon-carbon single bond, and there may be more than one possible ways or arrangement which are arising out of those sigma-sigma carbon-carbon bond rotation. Again, we can have the other part of the classification, that is configurational isomerism. The configurational isomerism again can be divided into two parts, but first of all, what is configurational isomerism? Configurational means the arrangement in space. So what we were talking of, the definition of stereochemistry, like the arrangement in space, the three-dimensional arrangement is the basic part of configurational isomerism. The difference in structure arises because of only the difference in arrangement of atoms in a molecule in space. There may be two types again, which are geometric isomers and optical isomers. Geometric isomers arise because of the carbon-carbon double bond. You may have learnt at the school level also that the geometric isomers give in alkenes the cis and trans and E and Z types of isomers. Last but not the least, the optical isomers are those isomers which arise due to their interaction with light, which is called as the plane polarized light. So, today I would be focusing my lecture on only optical isomers. Optical isomers we would be talking about. To start with, we should first know what is optical rotation. So, there was one scientist known as Jean-Baptiste Biot, who in 1815 discovered this optical rotation phenomena, and what he got was that there is light. We see light as in sciences we say that light can be given as two vectors perpendicular to one another. One is electric vector and the other is magnetic vector. They are oscillating in two different planes in 90-degree angle to one another. This is the definition of light which an organic chemist can give. Then what is plane polarized light? Like you can see the slide, it is light when passed through a nickel prism, or we can say it as a polarizer which consists of some nickel and cobalt material, and it becomes plane polarized light. What happens when light changes into plane polarized light? The light which was oscillating in all directions, as you can see in the picture, it changes from various planes, the three-dimensional sphere kind of thing, into one plane. Now, when the light is plane polarized light, it is only oscillating in one single plane. Then what should I do with this plane polarized light? What I do is I pass it through my organic compound, or for that matter any compound which may be optically active. It need not be an organic compound only, and when it passes, as you can see in the image, the light interacts with the matter, the solution we are having of the compound, and the direction of the plane changes in one direction only, and it goes on to give us that the final resultant is a rotation of the plane polarized light in either left or in the right direction. So, what does this suggest? It does not happen every time. It happens only when the compound you took was optically active. So, we would be learning what optically active means, but those compounds which are optically active, they give rise to optical isomerism, and the two isomers which are there, one rotates the light in left direction and the other one rotates the plane polarized light in right direction. The left one, which is rotating the light in left direction, is called as levorotatory, and the right one is called as dextrorotatory. So, these are the two types of isomers. The compounds are having same structural formula but different arrangement in space. We would come to that in a few moments, but we move to the next slide, giving you what is then optical rotation. Now, when I have talked about that optical rotation is the angle of rotation which is formed of the plane polarized light which was coming inside and then which is rotating to either towards the right side, left side or the right side. So, now we can see that there are two types of compounds which rotate plane polarized light either on the left or the right, and we are getting an optical rotation, a certain degree of angle of rotation, but this would certainly depend on the number of molecules present inside the tube. If I increase the number of molecules, the optical rotation increases, and if I decrease the concentration of the solution, the optical rotation decreases. So, for this purpose there was defined something which is called as specific rotation. What is specific rotation? It is you can see the slide, is the optical rotation of a compound when the length of tube and the concentration of the solution, or in case when the liquids are taken, density are unity. What does this mean? We can see also that this parameter is taken on a given temperature and a wavelength. So, you would understand by using this formula. I have put some formula here, which is alpha in square brackets is equal to alpha divided by C and L product. What are these? Alpha in square bracket is the specific rotation, and alpha, simple alpha, is the angle of rotation which came out from the polarimeter instrument you used. Alpha is the angle of rotation, C is the concentration of the solution, and L is the path length. Why we need specific rotation? We require specific rotation because we want to make that optical rotation parameter as a physical property. You can use specific rotation as a physical property, like you use melting point, boiling point, surface tension, refractive index, but in case of alpha as optical rotation or angle of rotation, you cannot justify that, because it would vary. If I take 1 gram of the compound, if I take 2 gram, it would double, if I take 3 gram, it would triple, and so on and so forth. So, for this purpose, what I have done, or what the scientists decided, was that we can divide that angle of rotation by the concentration, so that the number which comes out is a constant for all concentrations, and we need not bother if we are taking the specific rotation of a compound in India or in USA or in one instrument or in other instrument. So, we are fully acknowledging all the parameters, and it becomes a constant, certainly for a given temperature and a wavelength. Also, in certain instruments there are different length of the tube, the polarimeter tube, which we saw in the previous slide. The polarimeter tube length is also here as a denominator, so that this parameter is again nullified and we get an overall constant value for alpha in square bracket, which is called as specific rotation. But you should note that this specific rotation should be at for a given temperature and wavelength. Now, moving on to next slide, what I would like to discuss with you today is the history of stereochemistry. We always talk about stereochemistry as an organic chemist. We are always very excited to talk about stereochemistry because it involves models like this, and we talk about models and molecules and atoms, we visualize it and we say, wow, it is great. But we should give credit to the scientists who have done a remarkable job in every field, and we should acknowledge those things. So, as an organic chemistry learner and a teacher, I always like to introduce this concept of history of stereochemistry. How does this all evolve? And you would be surprised to see a few facts here. First of all, there was, as you can see the slide, there was a scientist, as I have already told you, Jean-Baptiste Biot. He was a French scientist who discovered the plane polarized light rotates when we interact with certain types of molecules. So, we should appreciate the capability and the mindset of these scientists, what they used to think. It was done in 1815. Now, I have divided this whole lecture into a few stories kind of thing. So, the first story starts with this scientist and going to the other one, which you all may be well aware of. He was Louis Pasteur. He was another person who was doing something else. He was not doing anything related to stereochemistry, but what he did was he knew that Biot had postulated that it is the optical rotation which is happening, a plane polarized light is rotating either to the left or to the right in 1815, and it was a well known fact. But while he was doing something related to his research as a postdoc, he was doing something with crystals of ammonium sodium ammonium tartrate, and he had an amazing observation. What observation he made? He made that observation that there were two types of crystals, because he was crystallizing, and we know that crystals have certain kind of shapes, and those shapes, he found that there are two types of shapes appearing in those crystals. So he decided to put those two shapes into different parts. But before, as you can see on the slide, he found that because he knew Biot's research, he found the optical activity of that mixture of crystals, and he found that optical activity was 0. Then using a magnifying glass and a pair of tweezers, he laboriously separated these two type of crystals. You can see on the slide that there are two kinds of crystals he explained. What I have made in this left handed and right handed. So exactly what was happening was that the two types of crystal, if you can see me, that there are two types of crystals which appearing. I have made left hand and right hand combinations, and those left handed and right handed crystals were present, and he separated those two forms and took the specific rotation of the two different solutions. Obviously, because we have talked about concentration, they were equimolar solution, they were of the same concentration, and bang, what he found was that one of them was rotating towards right side with an angle of 12.7 degree, and the other one was rotating towards left side, that is levorotatory, with the same amount of angle, that is 12.7 degree. So what does this mean? That this meant that the two isomers which were present in the system were not available to him in a proper manner. They were not available to him, they were not visible to him, but because of his efforts, because of his separation, he could differentiate and separate these kind of two isomers, the left hand and the right handed crystals. So he divided those two isomers, and when the optical rotation, he got the optical rotation of the two separately. There was certainly a fair amount of value of optical rotation with the same amount on right and left side in the polarimeter. Now what does this mean? What he got the inference out of it? He got what we today call as enantiomerism. You can see the slide I have written there. This paved way to the concept of enantiomerism, which is defined as the non-superimposability of the mirror images of a molecule. So non-superimposability and these enantiomerism concept, these we would be doing in a while. So the next point is that we would be doing is the last story of today, that is we have done enantiomerism, we have done how enantiomerism was coming into picture. We would be doing what enantiomerism is, how does enantiomerism goes on, and what are the criteria for that. But the dextro and levo, we have now found that Louis Pasteur was responsible for this. There were two great another scientists, and this is a altogether different story which I am going to tell you today. Do you know what is the geometry of carbon compounds, and when was it discovered? We all know, whenever you are there doing sciences in schools also, carbon and compounds are placed in a separate class, say organic chemistry we say, and there is a chapter in all junior level of classes, carbon and its compounds. And the first thing the teacher tells you is the geometry of carbon compounds is, primarily the geometry is tetrahedral. But when we came to know about this, we came to know about this in as late as 1874. Can we believe it? We were doing optical activity, we were doing enantiomerism like mirror images of the carbon compounds, and we were not knowing about the geometry of carbon atom, the tetrahedral carbon atom. So who discovered this? There were two eminent scientists, Van 't Hoff and Labelle. They discovered the geometry of tetrahedral carbon, albeit independently they were not working together. They discovered it in 1874. How did they do this? So I am taking this one molecule in my hand. This is I am not supposing that the geometry of carbon and its compound is tetrahedral. So I am saying that the geometry of a tetra covalent compound may be square pyramidal. So you can see that it is square pyramidal. This square pyramidal structure is having one yellow, this is the carbon, the blue one. The yellow one I am taking for any halogen, say chlorine, and the 3 are the hydrogens. So 3 hydrogens plus 1 carbon make it, what does it make? CH3Cl, chloromethane or methyl chloride. So Van 't Hoff and Labelle proposed that if we are having tetravalent structure of carbon, there are only possibilities of 3 types of structures or geometries possible. One is this square pyramidal, and if you bend it like this, it becomes planar and it is called a square planar, and the other one may be a tetrahedral geometry. These 3 types may be possible, but they have to identify which was they took this as a task, and what did they do? They used what is called as isomer number rule. So there is no discrete rule present as isomer number rule, but we can define it as the possible number of isomers present for a given molecule. So when they took this methyl chloride, I told you methyl chloride they were using. So when they identified, they found only one isomer of methyl chloride, but it was not a very important aspect, because in any case if we are having square planar structure or tetrahedral, we would be again getting only one isomer of methyl chloride. But when we change this one of this hydrogens with another chlorine here, we have taken another chlorine here, and now we get dichloromethane, 2 hydrogens, 2 chlorines. So CH2Cl2, we have got this. If it was a square pyramidal structure, we would have got 2 isomers. How come? First isomer is visible to you, the 2 chlorine atoms and the 2 hydrogen atoms are adjacent to one another. The second one we can get if we can change this into, I can change one of the hydrogens to with the chlorine atom. Now what is happening here? The chlorine atoms are in opposite directions. So this square pyramidal is having chlorine atoms in opposite directions and the hydrogen atoms are in opposite direction. So if you remember the concepts of coordination chemistry you did at the school level, you did coordination chemistry, we used to have the cis and the transforms which may be possible. So this is the transform of the square pyramidal structure, and the previously which I made was with the adjacent 2 chlorine atoms, which was the cis form. So if the carbon was in square pyramidal geometry, or for that matter in a square planar geometry, then there should be a presence of 2 isomers of dichloromethane molecule. So I suppose that it is clear to you. I would elaborate on a few facts more. The point is, you may question me, or for that matter Van 't Hoff or Labelle, that sir, it is not possible, it might be possible that we have not isolated the other isomer. But my dear friend, we have n number of thousands and lakhs of organic compounds, and we know each and every stereoisomer, we know each and every isomer. So this seems to be the most remote possibility that they would have missed the another isomer of dichloromethane. So taking into stride that now we have X-ray crystallography happening and everything happening, we know that carbon is tetrahedral. But look at the the significance of this discovery at that point of time when there were no such instruments available. By the mere fact that the second isomer is not available, we decide that, or Van 't Hoff and Labelle claimed and successfully claimed that the geometry of carbon is tetrahedral. So, we now consider the geometry of carbon as tetrahedral, and this would be further endorsed in today's lecture when we talk of the enantiomerism, the optical activity, or other points that if the structure, by the way, was not tetrahedral but say square planar, then the molecule would have been a planar molecule, and if would have been having a plane of symmetry, and there would not have been any enantiomerism existing. So, in this course of the isomer number rule, Van 't Hoff and Labelle not only proved that the tetrahedral carbon was present or the geometry was tetrahedral, but also paved way for the proofs and things for the optical activity. Now, moving further, I take you back to the point we left. So, this is all about the historical perspective of stereochemistry, and now we would certainly like to have a go on enantiomerism. So, for enantiomerism, we coined a term chirality. Very easy. Teacher comes and say that certain number of compounds are chiral, so take them as they are optically active, and those compounds which are not chiral, they are optically inactive. What do we mean by chirality? Chirality is nothing but the absence of symmetry, because I have already told you at the starting of the lecture that we would be talking about the visualization of the molecules. Say you should be able to see the molecules, dream the molecules and visualize them without these models. You should see the molecule as it is flowing or it is rotating in the air. So, for that we should understand that one term which is called as symmetry. Chirality is antagonistic or antonym to symmetry. If symmetry is present, the molecule is said to be achiral, and if symmetry is absent, the molecule is said to be chiral. So, I would again take you to the slide which says that symmetry comes when you can divide the molecule into two equal halves. So, I have taken one example here, dibromo, like we did the dichloromethane we take, and in this case we are taking it as dibromomethane. So, dibromomethane, because of the fact that it has a plane of symmetry. So, you can see here that these two chlorine atoms, if they are in one plane, I can divide this molecule into two equal halves. From this side, I can divide the molecule into two equal halves. The one half is having one hydrogen, half of the chlorine atom, this one half of this chlorine atom, and the other half is having this behind wala hydrogen and the halves of the chlorine atom. So, as this is given in the slide, these two dibromomethane, the second one, the first one is dibromomethane. I have taken the mirror image of that dibromomethane. Now, what I do this 180-degree rotation of the second wala dibromomethane. What I get? I get this one. So, when I try to superimpose, try to remember the earlier slide, I talked about Louis Pasteur experiment, and I told you that we need to have, for enantiomerism to exist, we need to have the non-superimposability of mirror images. But what is happening here? This bromine dibromomethane structure and the other dibromomethane structure which I formed by the rotation are superimposable. That means the point I tried to make with the model in my hand was that this molecule can be divided into two equal halves, and this molecule is symmetric, hence it is achiral, hence it is optically inactive. So, you can look at the slide that the achiral molecule or the molecule which is lacking, which is having symmetry, is optically inactive and is superimposable on the mirror image. But why I am telling you this about chirality? Chirality needs, the second slide says that if I change the groups with 4 different groups, I put one in place of one of the hydrogens I have taken as fluorine, and in place of another one I have taken what I have taken, fluorine. Fluorine, chlorine, bromine and hydrogen are the 4 atoms which are placed there, and these 4 atoms make the molecule asymmetric. Why it is asymmetric or chiral? Because when I take the mirror image, I take the mirror image here, and when even if I rotate this mirror image by 180-degree rotation, as in the previous case, I rotate it this way, and when I superimpose the two, I am not able to superimpose the bromine and the chlorine, although hydrogen and fluorine with their respective bonds are exactly superimposed. So, what I am trying to suggest here is that chirality is something which is absence of symmetry in the molecule. Absence of symmetry arises because of the fact that the 4 groups are different here. So, when I am teaching in my class and beyond this PowerPoint presentation, I talk about stereochemistry and talk about, say, your enantiomerism. I tell my students that you have got what is called as a tetrahedral carbon with you. This is a tetrahedral carbon. So, if I am visible to you clearly, this thumb, the finger, the middle finger and the arm represent 4 type of groups. Now, look how the nature is. Nature gives you tetrahedral carbon, which you have seen the definition as pointing towards the opposite corners of a cube or a room which is cubical. This is a tetrahedral carbon, and the nature has provided you with a chiral molecule in your hand, because you have all the lengths of these objects which I am talking about, my hand, are different. So, because they are different, you say that all the 4 groups are different, and you cannot divide this hand. Please do not try to divide it, because it is your own hand. So, you cannot divide this into 2 equal halves. Why? Because it is asymmetric. This symmetry is absent in this molecule. Like you would remember that there is, like, this hand or the palm structure is given in your books in 9th, 10th, 11th, 12th books. It is given, you cannot divide into equal halves. So, these 2 are mirror images which cannot be superimposed. We all have learned this, but you must know that God has not only given you one chiral center, but also given you the enantiomer of it. So, you can make the mirror image here, and when you try to superimpose, although we cannot do it because we cannot take out this joint and put it on there, but even if we could have done this, even if we could have taken these kind of models and you try yourself, you can, if you do not have models, you can use a simple clay and matchsticks to prepare these kind of models with different colors, and when you try to superimpose, they would not superimpose if all 4 groups are different. So, one way of saying this is that all 4 groups are different, and hence there is absence of symmetry. The other point which I want to make here is that we have reached to this point where the bromochlorofluoromethane is non-superimposable on its mirror image, and hence the molecule is chiral. But there needs to be a point which needs a mention here, which is that the carbon in this molecule is called as a chiral center. So, there are 2 terms, chirality for a whole molecule and chiral center for the carbon which is attached to 4 different groups. So, one point which I need to mention here, and it is very important, is that we do not need chiral center for the optical activity. We need a chiral molecule for optical activity. Am I trying to confuse you? No. What I mean to say is that we require in absolute terms, the absence of symmetry in the molecule. Even if there are molecules which have chiral centers, but they still be optically inactive, we would learn that. And even if there are no chiral centers, we have molecules in literature and they are present in chemistry labs which may be optically active. You would be learning those things in higher classes, maybe in the post graduation, and you would be learning those things. They are examples of allenes or spiro compounds and so many other compounds which do not have a chiral center, but still they are optically active. So, optical activity does not require the presence of a chiral center, but the presence of chirality for the whole molecule. We need a molecule which is asymmetric, or we can say that which is having no symmetry. Thus, we have the 2 enantiomers. Here the description we can give, and you must be doing it these 2 mirror images are called as enantiomers and they are non-superimposable. These 2 molecules are completely independent molecules. What do I mean by independent? Independent means that these 2 molecules are isomers and the isomerism is arriving because of the arrangement. You can see with my hand, if I can take this, say chlorine is coming towards you in the slide. In the first picture, chlorine is coming towards you. I take this chlorine off and I get a planar kind of molecule which is something like this, and this kind of this thing, and I introduce the chlorine on the other side. So, chlorine taken off and put it on the other side, I get the another enantiomer. So, by breaking a bond and placing it on the back side, I can get the other enantiomer. These 2 isomers are separable, they exist differently and have similar chemical and physical properties. We would be learning in future that how they may be separated. It is very difficult to separate them because of the fact that they have similar chemical and physical properties, right. So, this is all about chirality. Now, the next point comes, how can we define chirality? Chirality can be defined by the absence of symmetry in the molecule, or we can say that if we cannot divide into 2 equal halves. If I cannot divide a molecule into 2 equal halves, I can say that the molecule is chiral and the molecule is optically active. I have written here the line I have already told you that presence of chiral center is not a sufficient criteria for saying that the molecule is chiral or is optically active. Now, what is the way we can check the molecule is symmetric, achiral or not? That means molecule is asymmetric or chiral. So, there may be one way, like we have already done mirror image superimposability, we have already done. The other way may be checking for symmetry elements. Symmetry elements are a certain kind of operations, or we can say that certain type of rotation and reflections of the molecules. We can check whether the molecule is symmetric or not. So, we would be defining today 4 types of symmetry elements. We can see how much we can go far. The first one is simple axis of symmetry, CN. What is simple axis of symmetry? Simple axis of symmetry is when a molecule is rotated by an angle of 360 degree divided by n. I would be defining what n is, 360 degree by n angle we have rotated around an axis, and an arrangement which is similar to the original. Similar to the original means that we are saying that it is not exactly similar, it is not the same one, but similar. So, you would get when I would explain you with the example. First of all, you should know what is n here. N is the number of times we repeat the operation, and the number of times we repeat the operation n times we get the exact original. So, I would be explaining what exact original and similar to the original is. The proper axis of rotation Cn can be n is equal to 1 when the angle is 360 degree. If anything in this world would have n equal to 1 wala axis, because of the fact that if you rotate a thing by 360 degree it comes to the same, right. So, present in every molecule, or for that matter in everything in this world. N is equal to 2 180 degree rotation, 3 120 degree rotation, 4 6 and so on. If the molecule can be rotated indistinguishable to the original thousands of times or infinite times, we say that n may be equal to infinity. As in case of alkynes, you may learn that on your own, but we would not be needing that n is equal to infinity here. The maximum number of n wala axis, that Cn, is called as the principal axis of rotation, which is the highest order of axis present. So, I cannot take the examples of all the possible things, but I would certainly like to give you one example with again methyl chloride. We talked about methyl chloride. So, what you can see here is the chlorine and the red hydrogen, they are coming in the plane of the paper. So, in some other class we would be again defining what types of projection formula we need for the projection of the 3-dimensional structure into 2-dimensional form. Here what I have used is the wedge dash formula. So, the red hydrogen is in the plane of the screen you are watching, the chlorine is in the plane of the screen, the hydrogen is going behind the screen because it is shown by dash, and the green hydrogen, the blue hydrogen is shown by a black solid wedge, it is coming out of the screen. So, what I am trying to suggest here, that although that the 3 hydrogens are same, we know that the 3 hydrogens are same, still I have marked them as different kinds of colors, because to show that they may be used to identify what was similar to the original and exact original. So, my definition continues. What I am doing, I am rotating, say this is a kind of chloromethane, right, methyl chloride. The 3 hydrogens, I have not intentionally I have not placed any colored carbon, because it would give you an appearance of a chiral center. So, I have not given you different colors, because hydrogens are same, but in the slide I have placed green, blue and red. So, what I am doing? I am doing a 120 degree rotation. When I am doing a 120 degree rotation, either this way or this way, I am getting original in the sense that the 3 hydrogens, because they are all hydrogens, they are replacing one another and you are getting the same thing. But when you go back to the slide, you would see that when I am rotating it, my red hydrogen, which was in the plane of the screen, goes behind the screen and the green one comes ahead, and further when I do this 120 degree rotation, I get another one, the blue one going behind and the red one coming ahead and green one, and when I do the third time, I get exactly the same as I made I or original. I or E may be given for the original, the one we took initially. So, what I am trying to suggest here is the fact that there is an axis. If you can see the model in my hand, there is an axis which is passing through this chlorine and the carbon in this manner, and with this axis, when I am rotating this molecule like this, I am getting 3 forms with different colored hydrogens, although they are hydrogens and they are similar to the original, but I have marked, because of the fact that I have marked them with different colors, I am taking one hydrogen at a time, like my HA, HB or HC, you can mark like that also. HA is moving to the other one place, and then it is coming here, and then it is coming to the original. So, I have taken 3 rotation to make the original one. You can do similar things with ammonia also. Ammonia has this type of shape. When you rotate ammonia like this, the 3 hydrogens will give you the 3 types of rotation, and you would get, after the third one you would get the original. So, why I am again and again stressing on 3 number? Because 3 was your N here. N was 3 because I have taken the rotation by 120 degree. 120 degree, why? Because 360 degree divided by 3 gives you 120 degree, and you get a rotation of 120 degree 3 times gives you the same or exactly the same original wala molecule. So, this is the first type of symmetry element which I was talking about. Like the first type of symmetry element says that the axis of symmetry is that imaginary axis through which we rotate the molecule n number of times, we get exactly the original, and by the angle 360 degree by n gives you the similar to the original, or sometimes in books it is written indistinguishable from the original, because of the fact that hydrogen is replacing the hydrogen. I hope that I am clear on this. Now, moving on to the next symmetry element. For treating the chirality concept and the stereochemistry of enantiomers and all, we may not use much of the axis of symmetry, but because I am talking about symmetry elements, I have to deal with it, and you need to know what a symmetry axis, proper symmetry axis is. So, I talked about Cn. The second point is plane of symmetry. Plane of symmetry may be defined as a plane which divides the molecule into 2 equal halves. This is pretty important, because now you can see in the slide that we are writing here, thus the 2 halves are the mirror images of each other. So, can we go back to the enantiomerism concept and have a thought on this, that the mirror images concept is coming here in the symmetry element. So, certainly it has to do something with the chirality. Obviously, it has to do, because we are talking about symmetry and chirality is absence of symmetry. So, what is a plane of symmetry? So, I would be talking about the 2 types. You can see in the slide, there are 2 types of this operation happening. The 2 types of operation are the sigma. I missed one point, that the plane of symmetry is given by sigma, a Greek letter sigma, and the 2 types are sigma h or horizontal plane of symmetry. So, what is horizontal plane of symmetry? You can see in the image that this is an alkene molecule. I took it as trans 1,2 dichloroethene, but if you take it as simple ethene, or for that matter all 4 different groups, you would find that there is a plane of symmetry which is existing in the plane of the molecule. The molecule is planar itself, and that plane of symmetry is called as horizontal plane of symmetry. So, horizontal plane of symmetry we can define like, you can place these 2 your arms on one another, and you are having a double bond, you are forming a double bond with these 2 arms, and these 2 fingers and the thumb, they are coming as the hydrogens of the ethene molecule. So, this thing is whole planar. This plane, because it is horizontal, it is called as sigma h. The second type of, so this plane would, even if it was not in the ethene molecule, it would divide, you can see in the slide, it would divide the molecule horizontally in 2 equal halves. In this case, there is nothing above or nothing below, because of the fact that it is a planar molecule itself and it is coming in the plane only. The second type of the plane of symmetry is vertical plane of symmetry. Again going back to our best example, we have been talking about methyl chloride or chloromethane. We have a plane of symmetry existing in chloromethane. So, you can again come back to this model and you can divide this molecule by placing a plane like this. You can divide this molecule as we did for the Van 't Hoff and Labelle experiment. You can, this is coming towards you, one hydrogen is coming towards you and the other hydrogen is coming the other way, and this hydrogen, chlorine and the carbon are in the plane of symmetry, which we called as the vertical plane of symmetry. So, we did it in case of dichloromethane also. We divided, even if it was the other chlorine atom here, we easily divided it into two equal halves and this molecule can be divided by a vertical plane of symmetry. So, these are the two examples of plane of symmetry. So, I suppose that you must be correlating. It is very important here to mention that you should correlate the plane of symmetry or the other symmetry elements with the concept of enantiomerism. We need to correlate those things because at the end they would be coming at the same place. So, this is again I have written that a vertical plane dividing the chloromethane molecule in two equal halves. So, the next point is center of symmetry. So, center of symmetry is the center of symmetry or inversion center, it is called sometimes in a molecule, is such that if an atom is joined to it and this line is extrapolated to the other side, we find the same atom at the same distance. You can see that I have made one example here, and in this example here this black dot is the center of symmetry or inversion center. If from this point I move to this direction, I find a carboxylic acid group or the carbon of the carboxylic acid group, and I extrapolate this to the other direction, I again find the carbon of the carboxylic acid group. Same if I go from this exact distances from this point to this hydrogen, I find the other hydrogen at the same distance in the other direction. That is why I have written one another line to explain you in a better manner that we can say that it is a point such that we would find the same atom or group in either directions at equal distance. This is not a bookish kind of definition, this I have given you in a simple terms such that you can understand it, that if we move from this point to this OH, we would find OH at a certain distance, and if we move in the other direction, we would find the OH in the other direction at the same distance, and we may draw a line passing through this point from the OH to the other hydroxyl group. So, I have written here that in the above isomer of tartaric acid, the dot is exactly at the same distance from two hydrogens, two hydroxyl groups and two carboxyl groups, right. Then last but not the least, there is alternating axis of symmetry. I know that giving in the online form the lecture here, it is quite difficult to understand the alternating axis of symmetry because it needs two operations at the same point of time. Like if a rotation of 360 degree by n followed by a reflection in a perpendicular axis is done and it gives the original arrangement, the molecule is said to have Sn. I have again taken one example which is again of tartaric acid, the previous example. I rotate it by this 180 degree at this axis. So, it is not a axis of symmetry which we talked about, the principal axis of symmetry or simple axis of symmetry. I rotate it 180 degree using through this line which is dotted line I am showing here, and we get the other way round of the formula. Then I take a reflection perpendicular to that axis, perpendicular to this axis is perpendicular, and when we take this we get that this is original. So, finally I would like to conclude on this slide that We would be doing in the next lectures, we would be talking about enantiomerism and chirality, but I would give you the identification of symmetry elements. We talked about Cn, sigma, I and Sn. So what is the criteria we were talking about? We were talking about the criteria that if the symmetry elements are absent, the molecule is said to be chiral. So this is another way of saying that you can see on the slide that absence of symmetry elements sigma, I and Sn gives you that the molecule is chiral and is optically active. Or simply we can say that even if you can understand what Sn is all about, it is a little bit tough, but you can understand Sn, then if Sn is absent, then we can say that the molecule is chiral, because Sn includes sigma and I as S1 and S2 respectively. So thank you very much. We would be talking about this in the further lectures.
Thank you very much, sir, for a very interesting lecture with all the models, and definitely we would like to learn more about the Sn and sigma concept as regarding to the reactions, and definitely it was a very helpful lecture. Students, if you have any queries or questions, please do write into us, and you can definitely catch up this lecture at the YouTube channel. Thank you.